What in the world are viruses? Written by Cassandra Van Drunen-Lachance, Yi Yang Fei, Tim Chapman, Rico Kukako, Chetrini Tandon, Cameron Kabirbach, Christina Nguyen, Brianna Bedran, and Noah Varghese. Edited by Grace Nazavoa Zulu Sitima. Narrated by David Henneberg. Chapter 9. Future Research and Applications with Viruses. Written by Noah Varghese. If we learned anything from the COVID-19 pandemic, it is that learning about viruses as a pathogen is of utmost importance. The novel properties and intrinsic diversity of viruses make it a topic of study in the field of healthcare. The novel properties in question include its ability to undergo rapid mutagenesis, replicate rapidly, insert itself into the genome, and take advantage of cellular machinery in novel ways. Therefore, it isn't of any surprise that the field of virology was paving way for new technology even before the pandemic. This chapter will explore current research projects investigating viruses for their properties and regarding their potential application in several fields. The chapter aims to offer a summary of the said projects and encourage readers to investigate some of these topics in their own time. Novel sensors and detection protocols. To discuss the novel technology used to detect the coronavirus, we must first discuss the background and obstacles with current viral detection strategies. A virus's most defining feature is its microscopic size, where it can have a diameter ranging from 20 to 400 nm. Current virus detection usually involves extracting the virus from the sample, that being the infected tissue or a fomite, and then culturing it within a cell line. The mechanism of detection depends on the nature of the virus, such as what cell type it infects and how it infects it, but amongst all detection procedures, there are some similarities. For example, to detect influenza, the virus is exposed to the maiden-Darby canine kidney A549 or rhesus monkey kidney cell lines. Then after several days, it is then exposed to erythrocytes to see if the virus absorbs to the red blood cells. The absorption of the viral particles to the erythrocytes can be detected through antibody staining and immunofluorescence microscopy, which involves tagging a fluorophore, a chemical that can emit light under certain conditions, to that of an antibody, which is a biological molecule that binds to the virus. Antibodies can be designed in any means, but they are often naturally created by exposing mice to the virus, which its immune system will naturally create monoclonal antibodies that have the specificity to bind that specific strain of the influenza virus. Note that since influenza rapidly mutates, the antibodies created from influenza one year will probably not bind to the virus from another year. For Ebola, the gold standard wasn't necessarily reliant on culturing but on PCR, but instead on using reverse transcription PCR, which in layman terms involves more genealogy study. RT-PCR benefits stem from its ability to amplify low viral titers, thereby making the test incredibly sensitive. One new detection strategy of many viruses, including that of COVID-19, is the use of graphene working with biosensors. Graphene is a light, structured, carbon-based nanomaterial that is also highly electrical and thermally conductive. It can also take on many forms, such as a nanotube or carbon dots, although these structures are notably
Sample complete. Ready to continue?